Hey all Algebra 3 students. Today we're going to be learning about section 2.3. It's all about functions and something called relations too, and determining whether our relations are functions and also determining the domain and ranges of our relations. Okay, here are some definitions. A relation is any set of ordered pairs or points. And then a function it's still a set of ordered pairs, but it has these characteristics about it. Each of the first components, the input, corresponds to exactly one second component. That's very important right there. The input corresponds to only one output. Okay, so here I have examples for you. Notice that in this relation right here, it is a function because all of my inputs go to exactly one output. And then this relation here is not a function because right here, first off, this person, Tom, has the ages are going to two numbers. Well, this person, Tom, cannot be 21 and 22 at the same exact time. So that's a good way of noting that this is not a function because one x value cannot go to two different y values. Okay, that's how we're going to look at our set of ordered pairs in the next slide. So here are two relations, and we are asked to tell whether if it's a function or if it's not a function. So a good way to do this is draw a table of values of what you have here. These are my x values, these are my y values. So in a table, I'm going to draw x and y. And then I'm just going to put my x values in order because I like to do it that way. You don't have to. And then my y values in order. And then draw the lines that correspond to each of these numbers. So my 0 went to 7 down here. My 3 goes to 2, 5 goes to 0, and 6 went to -1. Notice that each one of my inputs, my x values, all of these x values went to exactly one y value. There's no repeated y value for any one x value. So this right here is a function. Now let's look at this relation that I have down here. Let's do the same thing. Write your x and y values. So -1, 2, and 4 are my x values. And then I have y values of 1, 3, 4, and 5. Now let's write our corresponding values to each other. So -1 went to 3. 2 goes to, 4 and 5. And then 4 went to 1. Okay, so this right here, this number 2 is going to 4 and 5. This tells you that it is not a function. So not a function. Okay. Here is something else that is going to help us in determining whether a relation or a graph of an equation is a function or not a function. It's called the vertical line test, and how the vertical line test goes is you can draw a vertical line through any part of a graph, and the vertical line intersects. If it intersects the graph of your relation only once, then it is a function. But if it intersects that graph of your relation more than once, it is not a function. let's look at this example here. Using the vertical line test, we're going to state whether this graph is a function or not. And using that vertical line test, I can draw a vertical line at any point on this graph. And it will never intersect this graph twice. It only intersects this graph once. See? Once here for that line, once here for this vertical line. So it never intersected it twice or more than once. So this is a function. Okay, let's move on to the next one. For this example here, I have a parabola drawn, and we can draw a vertical line through any vertical line through this relation, and it will, again, it'll never intersect this graph twice or more than once. So let's say this is a function because it passes the vertical line test. Okay, a graph of an ellipse. Well, this right here, if I draw a vertical line, it intersects the graph right here and right here. So for this relation right here, it is not a function because it does not pass that vertical line test. Okay? Now we're going to move on to something called domain and range. To state the domain and range, domain, you have to remember, it's all the possible x values of your relation that you have here. So here is my equation of the line that I have drawn here. It is a function, but no matter what, if it is a function or if it is not a function, you can still state the domain and range of that equation or relation. So domain, I'm going to do it darker here, domain. So remember, it's all of your x values. So domain, all the possible x values is what we're going to list. And since you can see that the graph of this function goes forever in this direction and also forever in this direction, it covers the whole x-axis, or in other words, it's all real numbers. So how we're going to state all real numbers is we can do it two ways. Right now, I'm going to say, you can state it in words, all real numbers, or you can use this symbol right here. But the way I eventually want you to do this in class is state it in interval notation. And we've learned about interval notation, and that is going to be like this. All real numbers means it goes from negative infinity to infinity. That's how it looks. Now let's do the range. Again, if we are looking at the graph of this function and we are trying to find the range, what we are going to be looking at is all y values, all possible y values that this relation has. Okay, so looking at it like this, well, from here up, the graph for all x values, it keeps going up for every y value. Well, it covers the whole y-axis going up, and same thing, going down. So you can state this same way as you did your domain. It's going to be all real numbers, or in interval notation, negative infinity to infinity. Now let's look at another graph. For this example, I've asked you to state the domain and range again, and just note by drawing this on your graph right here that it keeps going up forever, and that's going to help us figure out the range of this graph and also determine the domain. Just notice that as this graph goes up, it also goes forever in the right direction, and then same goes as it goes up in this direction, it goes to the left. So again, for this function, the domain, of this function is all real numbers, or in interval notation, you state it just like this: negative infinity, infinity. Now, let's look at the range. Range, you always look at the y values, and you start from the bottom of your graph and go up. Just like for domain, you normally start from the left of your graph and you go right. So just like you read the English language from left to right, that's how you're going to look at your graph, reading your graph for the domain too, from left to right. And then, so this graph right here, there is nothing below this point. There is nothing here. So where your graph begins is at this vertex, and then it goes up. Okay? So where your range begins is at that y value where the vertex is. So it begins at -4 and then goes up on, so we state that as infinity. And there you go, domain and range for this function. Okay, for this graph, I'm going to fill this in right here because it's supposed to be closed. It's a circle that goes all the way around and connects together right there. And for the domain, it's all of your x values. There is nothing past that point on this graph, or before -4. And then there is nothing after +4. So for that portion that I just drew in black, there are no x values for this equation. Where your x values lie are everything in between the circle, right? So the domain of this graph is going to be from, we're going to write it in brackets because we are including the points -4 and 4, but we write it like this: from -4 to 4. That is the domain. And the range is very similar for circles. Again, there is nothing below this point right here. I'll draw it in black. And there's nothing above this. Your entire graph of your equation here, the range of it is in between, again, -4 and 4. So state that. Range, again, from -4 to 4. For this function, the domain and range are a bit more difficult to state because we have something called vertical and horizontal asymptotes. And what I'm drawing in right now are those vertical lines that really are not supposed to be there. They are invisible lines. And here's our horizontal asymptote at the y equals 0, or on the x-axis. So this is our vertical and horizontal ones. Now, the graph of this function, what happens to it, let's start over here this direction. It keeps getting closer and closer to our x-axis, or y equals 0, as it goes further and further negative. But it never reaches x or y equals 0. It just gets closer and closer to it. Same goes off in this direction, the positive x direction. It keeps getting closer and closer to y equals 0, but never gets there. And then also for the asymptotes going up and down, it gets closer to the asymptote, the vertical asymptotes at 4 and -4, but they never reach it. So how we're going to state this is the domain for this function. You can see that it covers the entire x-axis except for at this point and at this point, but it covers the entire x-axis except for those points. So those are the points that we're going to exclude. For the domain, I'm going to write it out in words first. It's all real numbers. Sorry, can't get my pen to write correctly. It's all real numbers except, or you can say for x, oops, not e, for x not equal to -4 and 4. And the way we're going to state this in interval notation is just like this. We start with our negative infinity, because it's all real numbers, except for -4, we're going to exclude it like this by putting a parentheses around it. If it was a bracket, then that means that number is included. And then we're going to union it, and then start back up with -4 to 4. See how I'm covering the whole x-axis? So negative infinity to this point here, and then -4 to 4. Then again, I'm going to make another union symbol and union that with 4 to infinity. So union that with 4 positive infinity. And there you go. There's the domain. Now the range is similar. We're going to look at it. Again, the range, like the domain, is being covered. The whole y-axis is being covered, except for at y equals 0. There's there's a little hole right here. Okay. So range, again, I'm going to state it in words. It's all real numbers for x not equal to 0. And the way we're going to state that in interval notation, again, start with negative infinity, go to the point 0 that we're going to exclude, and then union it back up with 0 to infinity, and we're done. So function notation is a more formal way of stating a function, and it's represented like this. We know our function is y equals something, but we can replace y with f of x. And whenever we are evaluating functions at an x value, this x right here will be replaced with a number or some other variable, and to state, oh, they want you to evaluate it at that x value. So what this means right here, evaluate f of 2, it means take this function that you're given and replace your x values with 2. So plugging in 2, f of 2 equals 3 times 2 minus 5, which is 1. Now we can do the same thing even with variables inside our parentheses here. We're going to evaluate the function at x plus 1. So our answer is just going to be another function that has x plus 1 within it. Wherever you see x in our function, we're going to replace it with x plus 1 and then simplify it. So simplifying that, you have to distribute. And after you distribute, you can get rid of the parentheses. And then combine like terms. and then we're done, because that's as simple as it gets. So that f of x plus 1 for this function is equal to 3x plus 8. And there, we are done with this lesson. So I will see everybody in class, and we will work on a lot of this stuff in class. Bye, everybody.